So, hello and welcome to a live session on this advanced section in the NPTEL course. Today we are going to discuss about the multi-phase reactors, the basics of the slurry reactor, and some modeling aspects of the slurry reactor and the rates of gas absorption, the transportation of the materials to the catalyst, some diffusion techniques, reactions, and wet law. So, the target is to the operate the reactor to decrease the resistance of the slowest step and to increase the efficiency of the reactor. So, what are the advantages? The advantages are the temperature control and the heat recovery. These are very easily achieved, and there is some constant overall activity, catalytic activity, which can be maintained by the addition of small amounts of catalyst. With each reuse during the batch reaction or constant feeding during the continuous reactions. So there is basically a schematic of the slurry reactor is shown below. So in modeling of the slurry reactor, we assume that the liquid phase is well mixed. The catalyst properties, the catalyst particles are uniformly distributed. The gas phase is in plug flow. Basically, this is used for the direct hydrogenation reactions. So basically the reaction steps, if you see for a multi-phase slurry reactor, the first step is the absorption from the gas phase to liquid phase at the bubble surface. The second step is the diffusion in the liquid phase from the bubble surface to the bulk liquid. So basically one reactant would be in gas phase, another reactant might be in the liquid phase, and your catalyst would be solid. So this kind of multi-phase reactions usually happen from the hydrogenation reactions. Okay. The internal diffusion of reactant in porous catalyst is the fourth step, and the reaction within the porous catalyst. Okay. So if you see in the Henry's law, the concentration of liquid phase is related to the gas phase concentration. So the concentration is partial pressure into Henry's constant. What is the value of Henry's constant? It is 0.00233 mole hydrogen per atmospheric pressure into decimeter cube. And the first step is the rate of gas absorption, the rate of hydrogen transport from the gas liquid interface to the bulk liquid, the rate of absorption of A is equals to KBAB into Ci minus Cb. Kb is the mass transfer coefficient for gas absorption. Ab is the bubble surface area, and this Ci minus Cb is the difference between hydrogen concentration at hydrogen oil interface and bulk concentration of hydrogen in solution. Okay. The second step is the transport to catalyst, bulk solution to catalyst. This particular transportation, so you have to calculate the mass transfer, the rate of mass transfer of hydrogen from the bulk solution to the external surface area of catalyst. Okay. First, the hydrogen needs to be absorbed. Then, after this particular gaseous hydrogen is absorbed in the liquid phase, then this absorbed hydrogen has to transfer to the catalyst surface. So this rate is KCAC into M Cv minus Cs. Okay. So Kc is the mass transfer coefficient for particle. AC is the external surface area of particle. M is the mass concentration of catalyst, and this difference Cv minus Cs is the concentration of hydrogen at the external surface area. This difference is there. Okay. The third step is the diffusion and reaction in the catalyst pellet. Internal effectiveness factor to calculate. So minus Ra actual rate equals to effectiveness factor into the rate at external surface concentration. The fourth step is the rate law. Now then the reaction actual rate equals to K dash into CLO to C. Okay, K dash into CLO equals to K is the specific reaction rate. So the rate of reaction at the external catalyst pellet surface is minus RA S dash equals to KCS. So if you assume that the overall rate of transport is at the steady state, then the rate of transfer from bubble will be equal to the transportation rate to the catalyst surface, which is equal to the rate of reaction in the catalyst pellet. Right? Then you have to equate this particular equations which we have already written, and then from that we have to determine the rate limiting step, and then this particular values. Okay? Then the rate limiting step we have to determine, which is basically the diffusion or resistance to and within the pellet at a particular loading of catalyst. Is this absorption resistance and diffusion resistance ratio. Okay. So in this today's we will discuss only about the study reactor. We will have to see the trickle bed reactor as well and discuss that later. Okay. So the rate limiting step we are going to determine, we'll see the CI by RA is coming as equals to the RB plus RCR by L. Okay. So this RB is basically gas absorption resistance. Slope is equals to RCR, RC plus RR. So there is this change, which is the intercept. This change is due to the slope and the catalyst weight M. Decreasing the gas absorption resistance, one might consider changing the spurger to produce more gas bubbles of smaller diameter. Okay, so this is the ratio, the diffusional resistance to and within the pellet at a particular loading of catalyst. Determined by the particular ratio is the RB by RCR. Okay, absorption resistance by diffusion resistance. And so RB by RCR. And so if you see here and put the values of RB and RCR, then you can get this kind of things like this kind of correlations. Like if M decreases, the combined resistance will be decreasing, which means Kc and eta will be increased. It means the combined resistance decrease by decreasing the slope. This is the inference. Okay, and then there are these various cases, like to determine the rate limiting step. When external diffusion is controlling, when internal diffusion is controlling, or surface reaction is controlling by varying the particle size. Okay, so if you see the particle size, if we decrease, the internal or external diffusion will be decreased. So if the particle size is decreased, both eta and Kc will be increased. Eta means the effectiveness factor, Kc is the mass transfer coefficient. So you'll be making things more efficient. So provided this is a diffusion control. So decrease the particle size, use more catalyst. If it's diffusion control. If it's gas absorption control, then use more catalyst. Okay, there are these kind of conditions or this kind of cases when by varying the particle size we can control if it's we can see if it's external diffusion control, internal diffusion control, or surface reaction control. If there are very small particles, then it will be usually surface reaction limited. So if it's small to moderate size particle, then usually it will be internal diffusion limited. Resistance will vary linearly with the particle size, and overall rate of reaction can be increased or decreased in the particle size. And if it's a moderate to large size particle, then external resistance to diffusion limited. RC equals to 1 by KCSE. Basically, particle size is the important thing. If the slope is 0 between RCR and dP, then it's surface reaction limited. If the slope is equals to 1, means it's y equals to mx, then it's internal diffusion limited, and if the slope is 1.5 to 2, then it means it's external diffusion limited. Yeah. So as we discussed, the particle size affects on the controlling the resistance. So basically what we consider that uh, if it's an external diffusion controlling, then we can control it via the starting speed. If it's internal diffusion controlling, then decrease the particle size. And if it's surface reaction controlling, usually for catalytic, heterogeneous catalytic and the kinetics calculations, we consider this thing only to reduce the particle size more and more. So surface reaction is basically the controlling. And there are these examples which we have to see. In the first example, the catalytic hydrogenation reaction carried out in a slurry reactor. Hydrogen gas is bubbled up through the liquid and catalyst at 121 degrees Celsius, and catalyst-sized particle is between 10 microns and 100 microns. Okay, the experimental data is given. Like, okay, determine the controlling resistance and stuff. So you have to solve it. And if you have any doubt, you have to discuss it. Okay. Okay. Since nobody has joined, I'll end the class here. Thank you.